Hi, welcome back to Chapter 1, Part 2. In this part of the lecture, we will be talking about acceleration. The motion that we looked at in Part 1 of this chapter was technically called uniform motion. And uniform motion is when an object travels in a straight path with a constant speed. And in this case, the graph of uniform motion will be a straight line. So we saw this graph a couple times in the previous part of the lecture, where we had three objects, A, B, and C, all with different speeds and starting at different times and places and so forth. But one thing all of these objects have is all of their graphs are represented by straight lines. And this means that all of these objects were in a state of uniform motion, meaning they were traveling at a constant speed. Now, what about if we had a different object and we graphed its position or distance versus time again, and instead of a straight line, we got a curved line like shown here? How would you describe the motion of this object? Well, remember what we learned in the last part of the lecture, that the speed of the object is equal to the slope of the line on the graph. So down here in the initial part of the graph here, we see that the slope is relatively small. So that means the object is going at a slow speed. Somewhere in the middle here, we see that the slope is increased. It's higher. So maybe we could call it a medium slope, meaning that the speed now is some medium speed or velocity. And then at the end of the graph, we can see that the curve is almost going vertical, right? So we have a very steep, large slope, which means the object is going fast. So what's happening here is the object is starting down here and it's traveling slowly. And then as time goes on, its speed is increasing faster and faster and faster. So what is this called? Anybody out there know what this type of motion is called? So the answer is acceleration. Acceleration is when the velocity changes. Now, before we talk about the specific definition of acceleration and, work with word problems and so forth and formulas, let's just get a sense of the difference between acceleration and velocity. So the question I'll ask you here is, can you feel velocity when it's uniform motion? So for example, can you tell when you're moving in a car that's going at a constant speed down the road? Well, you might say, of course I can. I just look out the window and I can see, trees and houses going by. All right, so let's say you have to close your eyes and now you can't look out the window. So now can you tell if you're moving? Well, you might say, yeah, I can hear the engine or I can feel the bumps in the road and so forth. So let's change things up and let's say the car is perfectly quiet inside or you've got some loud music playing so you can't hear the engine at all. And let's say the car is, a real fancy Cadillac or something like that that's got a real cushy ride, and you're on a smooth road with no bumps. So now, when you're cruising down the highway at a constant speed, there is no way, with your eyes and ears closed and so forth, there's no way you can tell you're moving, even if you're going 60 miles an hour. The same thing applies if you've ever flown in an airplane. In a jet plane, when you're up at cruising altitude, you're actually moving very fast. You might be traveling at 500 miles per hour, but if the flight is smooth and you're not looking out the window, you don't have a sense of motion at all, as long as you're moving at a constant speed. Just another thing to keep in mind here is that our Earth is, of course, rotating. It rotates every 24 hours. This defines our day. So if you live near the equator, which, we're sort of near the equator, we're in this fairly far south from the North Pole at least, on the equator of the Earth, the surface of the Earth is rotating at about 1,000 miles per hour. So right now, as you sit here and listen to this video, you are rotating around the Earth at probably 800 or 900 miles per hour. Now, do you feel that rotation? Do you have to hold on to your chair, your desk? Of course not. But it gets better. The Earth is orbiting around the sun, and of course it takes 1 year for the Earth to make a complete orbit or revolution around the sun. Well, it turns out we're moving around the sun at a speed of about 20 miles per second. That's about 70,000 miles per hour. Now again, let me ask you, do you notice this motion? Can you tell you're moving 70,000 miles per hour? No, of course not. Well, it even gets better than that. Our solar system, our Earth and our Sun and all the other planets, is orbiting around the galaxy. All right, our galaxy, we'll learn about galaxies later in the course, but it's a collection of stars. And our Earth, or our Sun, I should say, is just one of about 200 billion stars in the Milky Way. And our Sun and the solar system is slowly orbiting around the center of the galaxy, as shown in this animation here. Well, it turns out we're traveling through galactic space at about 500,000 miles per hour. That's 500,000 miles per hour. And of course, we can't feel this velocity at all, right? So by the way, next time, if you ever get pulled over for a speeding ticket, and the cop says, well, you were going 10 miles per hour over the speed limit, just tell them, hey, that's no big deal. We're traveling 500,000 miles per hour through space right now. And let me know if that gets you out of your ticket. All right, anyway, let's move on here and now change gears and talk about acceleration. Let's say we're back in that car. Now, let's assume the car, all of a sudden, the driver presses the gas pedal and the car quickly speeds up. Will you notice that? Of course, right? You can feel it. If you're in an elevator and there's no windows in the elevator, it's very difficult to tell that the elevator is moving. However, you can always feel when the elevator starts and stops because there is an acceleration. There's speeding up and slowing down, and you can feel, your body can sense that acceleration. And of course, one of the ultimate experiences of acceleration is when you're riding a roller coaster. There's extreme acceleration, and that's what makes the ride so exciting. So the point of all this is that velocity and acceleration are very different types of motion. So now let's talk about acceleration in a little more detail. So acceleration is the change in velocity per unit time. So acceleration can be calculated by delta v. Now you may be familiar with the delta sign. That's a Greek letter delta, which means a change in whatever variable is next to it. So we have delta v. So this means the change in velocity divided by the time duration of how long it took for the velocity to change. So it's really what acceleration is. It's the rate of change of the velocity or the speed of an object. So how do we calculate the change in velocity? Well, we take the final value of velocity minus the initial value of velocity. This is delta v on top, and we just divide it by t. Down here we see our race car starting slow, and you can see it pick up speed as it moves across the screen here. So this is an example of acceleration, right? The velocity of the race car is changing, right? It starts maybe at rest at 0, and it ends up going very fast by the time it gets over here. Now, what are the units of acceleration? Well, they cause some confusion at first, so we're going to do a couple examples here to make sense of the units of acceleration. So I told you earlier in this course that we are going to use meters and seconds for distance and time. However, for this example, we're going to mix that up a little bit, and we're going to use some more familiar units that you're certainly familiar with. So let's say you're in your car and you start from rest. So you might be at a stoplight and the light turns green. So you hit the gas and your car speeds up to 60 miles per hour in just 5 seconds. All right, this would be a pretty fast car. So we want to calculate what is the car's acceleration. So we're going to use these units of 60 miles per hour for speed and seconds because we're sort of familiar with miles per hour. So acceleration, remember, is delta V over the time. So the change in speed of the car is 60 miles per hour, right? Because we're going from 0 to 60. So the change is 60. And how long did it take? Well, it took 5 seconds to reach that speed. So 60 divided by 5 is 12. Now the question is 12 what? Well, on top we have miles per hour, and on the bottom we have seconds. So the acceleration of the car is 12 miles per hour per second. In other words, 12 miles per hour every second that it travels. So if we were to construct a table showing the time here, starting at 0 seconds, the car is going 0 miles per hour, of course, because we're at rest. After 1 second, we're going 12 miles per hour, because remember, the acceleration is 12 miles per hour every second. After 2 seconds, the car is now going 24 miles per hour. Remember that every second, the car speeds up by 12 miles per hour. So after 3 seconds, the car is going 36 miles per hour. We just keep adding 12 to these numbers. After 4 seconds, 48 miles per hour. And finally, after 5 seconds, we add 12 to 48, and we get the final speed, which is 60 miles per hour. So this kind of gives us a sense of the units of acceleration. The number tells us how much the speed is changing every second. So let's redo this same problem, but use meters per second instead of miles per hour. So if you Google or look up how to convert miles per hour to meters per second, you'll find that 60 miles per hour is equal to about 27 meters per second. So our problem now looks like this. A car starts from rest and speeds up to 27 meters per second in 5 seconds. What is the car's acceleration? So again, acceleration, A, is equal to delta V over T. Delta V is now 27 meters per second divided by 5 seconds. 27 divided by 5 is 5.4 meters per second per second. Well, instead of writing meters per second, we can sort of combine the two S's here, since they're both multiplied together, and we can write it as 5.4 meters per second squared. So the units of acceleration are meters per second squared. And that it's a little confusing, because what is a square second? That doesn't really make sense, right? What is time squared? Well, that's not the way to interpret this. What this really means is meters per second per second. So going back to our table now, again, we start at time 0. Our speed is 0 meters per second. After 1 second, remember our acceleration is 5.4 meters per second every second. So after 1 second, the speed is 5.4 meters per second. After 2 seconds, it's 10.8. We just add another 5.4. After 3 seconds, add another 5.4. We get 16.2. And after 4 seconds, 21.6. And finally, after 5 seconds, we arrive at our final speed of 27 meters per second. Let's look at a couple acceleration word problems. So the first problem says a car starts from rest and accelerates at 5 meters per second squared. How fast is it going after 3 seconds? So this problem is a little different. We're going to actually calculate the final speed from the acceleration which is given. And of course the time was given too. So let's look at our definition of acceleration again. A is equal to delta V over T. Remember, that's V final minus V initial. Okay, if I didn't explain this real well in the last slide, remember that the little f here just means this is the final velocity, and the I here means this is the initial velocity. So these are sort of these are called subscripts, and they are like name tags attached to these letters here, or these variables. Now, of course, the initial velocity of the car is 0 because it starts from rest. So we can get rid of this term. So the acceleration, A, is just the final velocity divided by the time. Now, we want to calculate or solve for the final velocity. So we have to multiply through by t to get rid of the t under here. So the final velocity is equal to acceleration multiplied by t, time. So acceleration was given as 5 meters per second squared, and the time was given as 3 seconds. We can do this in our head. 5 times 3 is 15. And notice we have meters here, and this s here cancels one of these two s's underneath here, so we end up with just a single s on the bottom. So our units are 15 meters per second, which is the final speed of the car. Part 2, how long will it take this car to reach a speed of 20 meters per second? So again, using our result from up here, acceleration in this case is final velocity divided by time, we can solve this for time. All right, so the time is equal to the final velocity divided by the acceleration. Now, how did I get from this step to this? Well, I actually had to do two different steps. I multiplied through by t, and I divided through by a. So that's all shown here in one swoop. So the time needed is final velocity divided by acceleration. So I have 20 meters per second is my final speed here, divided by 5 meters per second squared. Remember, that was the acceleration that was given to us. 20 divided by 5, again, we can do that in our head. It's just 4. And there's a bunch of units here, but notice the meters cancel, and this s here cancels one of those s's here, leaving just the one s down here. But since it's in the denominator of a fraction that's also in the denominator, the s comes back on top, and our answer is 4 seconds. So it turns out that acceleration can be positive or negative. So let's look at an example of a negative acceleration. Suppose you're driving your car at 15 meters per second and you slam on your brakes. Your car comes to a stop in 1.5 seconds. So this is shown down here in our little animation. So here's the car, notice braking, 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 and it comes to a stop here in 1.5 seconds. So in this case, we're going to calculate your car's deceleration, all right, which means you're slowing down instead of speeding up. So the good news is we can use our same definition. Acceleration is delta v over t, which is v final minus v initial divided by the time. Now, the final velocity in this case is 0, because notice the car comes to a rest. So v final is 0, so we have 0 minus v initial. This 0, of course, just goes away, and we end up with minus v initial on top. So we have negative 15 meters per second, right? That was the speed of our car, and we have that minus sign from right here. So we have negative 15 meters per second divided by the time was given as 1.5 seconds. And so this turns out to be negative 10 meters per second squared. So notice the acceleration here is negative. So what does that mean? Well, this is what happens when we have something slowing down or decelerating. And physically, what this number means is your speed is decreasing by 10 meters per second every second. That's why it's negative 10 meters per second squared. So far, all the problems that we've considered involved an object that started at rest, like when you're in your car sitting at a stoplight, and all of a sudden the light turns green and you press the gas pedal. But that's not always the case. For example, what if you're cruising along the highway at a steady speed and then all of a sudden, you know, push the gas pedal down? How fast are you going to be going then? Well, this is a little different, but we can figure this out, how fast you're going if you're already moving, by again looking at the definition of acceleration. Remember, acceleration is the change in velocity divided by time. So we have v final minus v initial divided by time. So let's rewrite this equation here into a form that'll be more useful for us. So let's multiply both sides of the equation by t. So on the left we have a times t. On the right, of course, we've gotten rid of this t because we've multiplied by t. So we have at equals v final minus v initial. The last step is we're going to solve for the final velocity of the object. Now, how do we do that? Well, that's easy. We just add initial velocity, VI, to both sides of the equation. So the result is shown right here, and this is the form that we're going to use. The final speed of an object is equal to the initial speed of the object plus the acceleration of the object times multiplied by the time of the acceleration. Okay, so V final equals V initial plus AT. So let's do an example using the formula that we just derived on the previous slide. This is an example when the initial speed is at 0. So a car is cruising at 15 meters per second. When it suddenly accelerates at 2 meters per second squared for 6 seconds, how fast is the car now going? So we're just going to use the equation from the last slide. V final equals V initial plus acceleration times time. The initial velocity is 15 meters per second. The acceleration A is 2 meters per second squared, and the time was given as 6 seconds. So this is 2 times 6, which is 12 meters per second. We're going to add that 12 to the initial velocity, which was 15 meters per second. 15 plus 12 is 27. So the final speed of the car is 27 meters per second. The last thing we're going to do in this part of the lecture is derive a very useful formula that I call the distance formula. So we've seen so far that distance and velocity are related. In other words, velocity is just distance divided by time. And we've seen that velocity and acceleration are related. Acceleration is the change in velocity over time. The question is, how is the distance that something travels related to the acceleration of the object if it's speeding up? Well, in order to figure this out, we have to, combine these two equations basically. And I'm going to skip over the results here because we're just going to use the result here, which is going to be useful. So the distance formula says that the distance traveled by an object that's accelerating when it starts from rest is equal to 1/2 a times t squared. Okay, now one thing, just this formula only works for objects that start from rest. So in this course, we're just going to consider objects that start from rest when we use the distance formula. In a more advanced course, there's another equation that is more complicated that accounts for objects that are already moving. So we're not going to do that in this course. So remember here that d is the distance traveled during the acceleration a for time t, and it's starting from rest. And just remember here that the t is squared. So in our last slide here of this part of the lecture, let's look at an example that uses some of these equations that we've encountered here, including the distance formula. So we've got a car that starts from rest, then it accelerates at 4 meters per second squared. Part A, how fast is the car going after 5 seconds? So let's do this one. Well, we know that the final velocity is equal to initial velocity plus AT. We can use this formula, and in fact it's not even that difficult because the initial velocity of the car is 0, so we can just scratch off that term. So our final speed is just acceleration, which is 4, multiplied by the time, which was 5 seconds. So 4 times 5 is 20. So our speed after 5 seconds is 20 meters per second. Part B, how far does the car go in 5 seconds? So here we're going to use our distance formula. Distance equals 1/2 a t squared. So we have 1/2 times the acceleration, which is 4. And again, the time is 5 seconds. But remember, we have to square the 5. So this is 5 times 5, which is actually 25. So the answer here, when you multiply these three terms together, you'll get 50 meters. The last part, how long does it take the car to go 100 meters? So in this case, we're going to use the distance formula again. Distance is equal to 1/2 a t squared, but we're going to solve this for the time, t. We want to figure out how long it takes. We know the distance here is 100. We know the acceleration is 4. We have to figure out what t is. So to do this, it's just a couple of steps. We have to get t all by itself. So to get rid of the 1/2, I'm going to multiply both sides of the equation by 2. So I get 2d equals at squared. To get the t squared by itself, let's get rid of the a, so I'm going to divide both sides by a. So t squared is equal to 2d over a. And finally, to solve for t, I just take the square root of both sides of the equation. So t is equal to the square root of 2d over a. Remember the d, the distance is 100 meters, and a, the acceleration, was 4 meters per second squared. So this is 200 divided by 4, which is 50, and then we have to take the square root of 50, so our final answer is 7.0 seconds. That's how long it takes this car to go 100 meters when it's accelerating at 4 meters per second squared, which is shown down here. Here's our car accelerating along. All right, you guys, that is it for this part of the lecture. I will see you shortly for part 3. Goodbye.